Hello there, and welcome to this quiet journey through time and space. I'm so glad you found your way here tonight. Perhaps you've had a long day, or maybe you're someone who finds peace in cosmic stories rather than counting sheep. Either way, you're exactly where you need to be. These clouds have been drifting for millions of years, shaped by stellar winds and the gravity of nearby stars. Some are stirred by the shock waves of distant supernovas, creating ripples that travel across light years like slow-motion tsunamis in an ocean of gas. The cloud we're visiting tonight has been disturbed by just such a wave, a gentle compression that started the most important process in the cosmos. Tonight, we'll follow a single star from its very first breath to its final rest among the cosmos. This is a story that spans billions of years, yet unfolds with the gentle patience of a lullaby. You have nothing to do but listen, letting your breathing slow and your mind drift as we travel together through the most beautiful transformation in the universe. We'll begin in the cold, dark nurseries where stars are born, drift through the long, peaceful years of stellar life, and witness the magnificent ways that stars give their gift to the galaxy when their time comes to an end. Some of what you hear tonight might surprise you, and some might simply carry you gently toward sleep. Both are exactly right. Before we begin, let your body settle. Feel the weight of gravity holding you softly in place, just as gravity shapes everything we'll explore tonight. Your breathing can slow, your thoughts can wander, because this story isn't told in minutes or hours, but in the deep time of the cosmos, where everything unfolds with infinite patience. Now, let's begin. Far out in the darkness between stars, where space seems empty and cold, something beautiful is stirring. Here, in the vast molecular clouds that drift through our galaxy, the ingredients for stars are gathering. These clouds are unimaginably large, sometimes stretching across hundreds of light years, yet they're so thin that the best vacuum chambers on Earth are denser. They're made mostly of hydrogen, the simplest and most abundant element in the universe, along with traces of helium and tiny dust grains no bigger than smoke particles. The temperature here is almost absolute zero, around negative 440 degrees Fahrenheit. It's so cold that if you could somehow visit, even the air you breathe would freeze solid instantly. But this extreme cold is exactly what's needed. In the bitter chill of space, atoms move slowly, allowing gravity's gentle touch to begin its patient work. Within the cloud, density varies like weather patterns. Some regions are slightly thicker, containing just a few more atoms per cubic inch than their surroundings. This tiny difference is enough. Where matter is slightly denser, gravity is slightly stronger. And gravity, patient and persistent, begins to draw more material inward. It's hard to imagine something so gradual. The collapse happens slowly, over hundreds of thousands of years. If you could watch from a safe distance, you'd see the cloud very slowly contracting, like a vast balloon deflating in the most gentle way possible. Dust and gas spiral inward in graceful curves, following paths carved by gravity and magnetism. The cloud doesn't collapse all at once. Instead, it fragments into smaller pieces, each destined to become a star. Think of it like a vast spider web covered in morning dew, where each droplet slowly grows larger and larger, collecting moisture from the silk around it. Our star is one of these droplets, gathering mass grain by grain, atom by atom. As material falls inward, something remarkable begins to happen. The cloud starts to spin. This isn't by choice, but by necessity. Just as ice skaters spin faster when they pull their arms close to their body, The contracting cloud rotates more and more quickly as it shrinks. What started as the barely detectable rotation of the original cloud becomes an elegant, swirling motion. The matter doesn't fall straight down toward the center. Instead, it spirals inward, forming a flattened disk around the growing core. This disk will be important later, for it's here that planets might one day form. But for now, it's simply a beautiful consequence of physics, matter dancing in slow motion to the music of gravity and angular momentum. At the very center of this cosmic whirlpool, our protostar is taking shape. It's not a star yet, not truly. It doesn't shine with nuclear fire, but it's growing warmer as gravitational energy converts to heat. Every atom that falls inward releases a tiny amount of energy, and with trillions upon trillions of atoms joining the collapse, that energy adds up. The temperature begins to climb. From the bitter cold of interstellar space, the core warms to the freezing point of water, then far beyond. The protostar glows dimly like a cosmic ember, radiating infrared light that human eyes cannot see. If you could somehow visit, you'd find yourself surrounded by a warm, glowing fog, lit from within by the gentle heat of gravitational compression. The protostar is enormous at this stage, much larger than our entire solar system. It's a vast, puffy ball of gas, still gathering material from the surrounding cloud. Jets of material sometimes shoot out from its poles, carrying away excess energy and angular momentum. These jets can stretch for light years, glowing streams of gas that announce the birth of a new star to anyone watching from afar. For nearly 100,000 years, the protostar continues to contract and heat up. The pressure at its core grows tremendous. Atoms are squeezed closer and closer together until the very structure of matter begins to change. Electrons are stripped away from their nuclei. The core becomes a soup of naked atomic nuclei and free electrons, a state of matter called plasma. Still, the temperature climbs. 1 million degrees, 5 million, 10 million. The protostar is transforming, shedding its outer layers of dust and revealing the glowing ball of gas within. For the first time, it becomes visible to optical telescopes, a faint red glow emerging from its dusty cocoon. And then, at 15 million degrees Celsius, something magical happens. The temperature and pressure become so intense that hydrogen nuclei, which normally repel each other with electromagnetic force, are squeezed close enough for the strong nuclear force to take over. 2 hydrogen nuclei fuse together, creating helium and releasing a tremendous burst of energy. This is the moment our star is truly born. Nuclear fusion has begun. The change is not dramatic from the outside. There's no explosion, no sudden brightening. But deep in the core, the star has found its power source. Every second, millions of tons of hydrogen are converted into helium. And in that conversion, a small amount of matter becomes pure energy, according to Einstein's famous equation. The star begins to shine with its own light. A delicate balance is achieved. Gravity pulls inward, trying to crush the star under its own weight. But the energy from fusion pushes outward, creating pressure that holds the star up against gravitational collapse. It's like a perfectly balanced game of tug-of-war, where neither side can win. The star settles into a stable, long-lived phase called the main sequence. Our star, now roughly the size and mass of our sun, will remain in this peaceful balance for approximately 10 billion years. That's nearly twice the current age of the Earth. It's a span of time so vast that entire civilizations could rise and fall, continents could drift across planets, and galaxies could complete multiple rotations. all while our star burns steadily and reliably. The fusion process is beautifully simple, yet profound. In the core, where temperatures reach 27 million degrees Fahrenheit, hydrogen nuclei dance in the extreme heat. When 4 hydrogen nuclei come together in a complex series of reactions, they form one helium nucleus. But the helium nucleus weighs slightly less than the 4 hydrogen nuclei that created it. That missing mass becomes energy, radiating outward from the core. The energy doesn't escape immediately. The star is so dense that photons of light bounce randomly from atom to atom, like a ball in a 3-dimensional pinball machine. A single photon born in the core might take 100,000 years to reach the surface, ricocheting countless times on its journey outward. By the time it finally escapes into space, the star's surface has become a roiling magnetic tapestry of convection and plasma. The surface temperature settles at about 10,000 degrees Fahrenheit, hot enough to vaporize any known material instantly, yet cool compared to the nuclear furnace at the core. The star's color depends on this surface temperature. Our star glows with a warm yellow-white light, the same comforting color as our sun. From a distance, the star appears perfectly steady, a constant beacon in the darkness. But its surface is actually alive with motion. Granules of hot gas rise from the interior like bubbles in a pot of boiling water, each one the size of a large country. Magnetic field lines, twisted by the star's rotation, break through the surface, creating darker spots and brilliant flares that dance across the stellar atmosphere. The star rotates slowly, once every 25 days or so. This rotation helps drive a magnetic dynamo in its interior, generating field lines that extend far out into space. Sometimes these magnetic fields become tangled and snap, releasing bursts of energy that would dwarf the strongest explosions on Earth. Yet these stellar tantrums are just tiny hiccups in the star's otherwise peaceful existence. As the eons pass, the star remains remarkably constant. It burns hydrogen at a steady rate, converting about 600 million tons of matter into energy every second. This sounds catastrophic, but the star is so massive that it barely notices this loss. It has enough hydrogen fuel to maintain this rate of consumption for billions of years. The consistency is what makes main sequence stars so special. They serve as reliable lighthouses across the galaxy, steady beacons that can nurture the development of planetary systems. Any planets orbiting our star would bask in consistent warmth and light, perfect conditions for the slow chemistry of life to unfold. Deep in the core, the helium produced by fusion begins to accumulate. Like ash in a fireplace, this helium doesn't burn at the core's current temperature. It simply settles toward the center, gradually changing the composition of the star's heart. This process is so slow as to be almost imperceptible, but it will eventually determine the star's fate. For now, though, all is peaceful. The star has found its rhythm, its perfect balance between the inward pull of gravity and the outward push of nuclear fire. It shines steadily through space, its light carrying energy and warmth to any worlds that might orbit around it. It's in the prime of its life, a mature, stable, reliable star that will continue burning for billions of years to come. The light streaming away from our star carries more than just energy. It carries the elements forged in the nuclear furnace at the core. When hydrogen fuses into helium, it creates not just energy, but also a slightly different form of matter. The helium nuclei contain 2 protons instead of hydrogen's single proton, making helium the second element on the periodic table. This might seem like a small change, but it represents something profound. Our star is gradually transforming the universe, converting the primordial hydrogen left over from the Big Bang into heavier, more complex elements. It's an act of cosmic alchemy, turning the simplest matter into something new. The fusion process is mediated by the weak nuclear force, one of the 4 fundamental forces that govern our universe. This force is so weak that even under the extreme conditions in the star's core, fusion proceeds very slowly. This is actually a blessing. If fusion happened quickly, stars would burn through their fuel in just a few million years. Instead, the weakness of this force allows stars to burn steadily for billions of years, providing the stable energy needed for complex chemistry and possibly life. Meanwhile, the star's outer layers remain in constant motion. Convection currents carry hot material from the interior to the surface, where it cools and sinks back down. This creates a complex 3-dimensional dance of flowing plasma that helps regulate the star's temperature and carries the products of fusion throughout its body. The star's magnetic field, generated by the motion of charged particles in its interior, extends far beyond its visible surface. This magnetic field creates a bubble around the star called the heliosphere, which deflects high-energy cosmic rays from other parts of the galaxy. Any planets orbiting the star would benefit from this magnetic shield, protected from the worst of galactic radiation. As our star continues its 10 billion-year journey through the main sequence, small changes accumulate. The helium ash in the core slowly builds up, making the core slightly denser and hotter. The increased temperature causes the star to burn hydrogen a bit more quickly, making it slightly brighter over time. But these changes are so gradual that they're essentially invisible on human timescales. The star also moves through the galaxy, orbiting the galactic center on a journey that takes hundreds of millions of years. As it travels, it encounters different regions of space, some richer in dust and gas, others relatively empty. These encounters can subtly influence the star's properties, but they don't fundamentally change its steady nuclear burning. Other stars may form nearby from the same original cloud. Our star might have hundreds or even thousands of siblings, all born from the same stellar nursery. Over time, these siblings drift apart as they orbit the galaxy, but they carry similar chemical fingerprints that betray their common origin. Somewhere among the stars, our star's brothers and sisters continue their own journeys through the main sequence. The star's steady output creates a habitable zone around it, a range of distances where liquid water could exist on the surface of rocky planets. This zone is sometimes called the Goldilocks zone because it's not too hot and not too cold, but just right for life as we know it. As the star very slowly brightens over billions of years, this habitable zone gradually moves outward. The nuclear reactions in the core create more than just helium. Occasionally, the fusion process produces trace amounts of other light elements like lithium and beryllium. The star also captures cosmic rays from space, high-energy particles that can split heavier nuclei into lighter ones through a process called spallation. All of these processes contribute to the slow evolution of the star's chemical composition. Yet, for all this subtle change, the overriding characteristic of main sequence life is stability. The star has achieved a perfect balance, a harmony between competing forces that allows it to shine steadily for eons. It's a testament to the beautiful physics of stellar structure, where pressure and gravity, heat and cold, creation and consumption all balance in perfect equilibrium. This stability is what makes stars like our Sun so precious. They provide the consistent energy that planets need to develop complex chemistry. They burn long enough for evolution to work its slow magic. They create the heavy elements that planets and life require, but they do so gradually, without the violent disruption that would sterilize their surroundings. And so our star burns on, a beacon of consistency in a changing universe. Its light has traveled for thousands of years to reach us, carrying the gentle energy of nuclear fusion across the vastness of space. Every photon that touches your face began its journey in the incredible heat and pressure of a stellar core, where matter transforms into energy in the most fundamental alchemy of the cosmos. But nothing lasts forever, not even the most stable star. Deep in our star's core, changes are taking place that will eventually transform this steady beacon into something far more dramatic. The helium ash continues to accumulate, and the hydrogen fuel slowly burns away. Our star is aging, though it will take billions of years for that aging to become apparent. For now, though, the star continues its patient work, fusing hydrogen into helium, converting matter into energy, and shining steadily through space. It has found its rhythm and settled into the long, peaceful chapter of stellar life, known as the main sequence. It burns with the quiet confidence of a well-tended fire, reliable, warm, and beautifully, perfectly stable. Time passes differently for stars than it does for us. What seems like eternity to human consciousness is merely a moment in stellar time. Our star has been burning for perhaps 5 billion years already, roughly half its main sequence lifetime. In the cosmic calendar, it's middle-aged, still vigorous, but no longer young. The galaxy rotates around our star as it pursues its orbit, and our star watches the slow dance of spiral arms passing overhead. It has already completed many orbits around the galactic center, each one taking 200 million years. It has seen the rise and fall of countless other stars, witnessed the birth of new stellar nurseries, and shone its light on the gradual evolution of the galaxy itself. Through all of this cosmic time, the star's fusion reactions continue with clockwork precision. The quantum tunneling that allows hydrogen nuclei to overcome their mutual repulsion happens trillions of times per second in the core. Each fusion event releases a specific amount of energy, and the accumulation of all these tiny nuclear fires creates the steady luminosity that defines our star. The energy produced in the core doesn't just flow outward, it also helps support the star against its own gravity through radiation pressure. Photons have momentum, and when they bounce off particles in the star's interior, they transfer that momentum and create an outward force. This radiation pressure is part of what keeps the star from collapsing under its own weight. As our star ages, very subtle changes occur in its interior structure. The accumulation of helium in the core makes that region slightly denser and hotter. The hydrogen-burning shell around the core responds by burning more efficiently. The star becomes very gradually brighter, though the change is so slow that it's barely detectable over millions of years. The star's surface also shows the effects of its magnetic activity. Star spots, cooler regions created by strong magnetic fields, come and go in cycles. Stellar flares occasionally erupt from the surface, sending bursts of high-energy particles streaming into space. These events are reminders that despite its overall stability, our star is a dynamic, magnetically active object. The steady nuclear burning creates a gentle stellar wind, a stream of charged particles flowing away from the star's surface. This wind is much gentler than the violent eruptions of more massive stars, but it still carries matter into space, very slowly reducing the star's mass over time. The mass loss is tiny, but over billions of years, it can become significant. Meanwhile, the star continues to synthesize new elements in its core. The fusion of hydrogen into helium is just the beginning of stellar nucleosynthesis. Under the extreme conditions in the core, helium nuclei occasionally collide and stick together, forming beryllium. Most beryllium is unstable and quickly decays, but sometimes another helium nucleus collides with it before it can decay, creating carbon. This process, called the triple alpha process, is much rarer than hydrogen fusion. It requires even higher temperatures and densities than our star currently possesses. But as the star ages and its core grows hotter, this reaction will become more important. Carbon is the foundation of organic chemistry, and its creation in stellar cores is one of the ways that stars prepare the universe for complexity and life. The star also produces trace amounts of other light elements through various nuclear reactions. When cosmic rays strike its atmosphere, they can create lithium, beryllium, and boron through spallation. The star's convection currents mix these elements throughout its outer layers, gradually changing its surface composition. All of these processes happen slowly, incrementally, as the star ages. The changes are so gradual that the star appears perfectly constant to any hypothetical observer. Its light remains steady, its temperature stable, its magnetic field regular in its cycling. It's a masterpiece of natural engineering, a fusion reactor that regulates itself through the elegant interplay of physics. The star's gravitational field shapes space around it, creating wells and curves in space-time that define the orbits of any surrounding planets. If our star has planets, they orbit in stable, predictable paths, locked in gravitational embrace with their parent star. The star's consistent output provides them with reliable energy, while its magnetic field helps protect them from harmful cosmic radiation. As the star moves through its orbit around the galaxy, it encounters regions with different densities of interstellar matter. Sometimes it passes through spiral arms rich with gas and dust. Other times it traverses the quieter regions between arms. These encounters can subtly affect the star's properties, but they don't fundamentally change its steady burning. The star is also influenced by the gravity of its stellar neighbors. Close encounters with other stars are rare, but not impossible. When they do occur, they can perturb the orbits of any planets and stir up the star's outer layers. But the nuclear furnace at the core continues burning regardless of these external influences. Our star represents one of the universe's greatest success stories. It has achieved a nearly perfect balance between opposing forces, allowing it to burn steadily for billions of years. It converts matter into energy with remarkable efficiency, creating light and heat that can warm planets and power the complex chemistry of life. The star also serves as a cosmic lighthouse, a reliable beacon that can be seen across vast distances. Its steady light carries information about its composition, temperature, and age to any astronomers who might be watching from afar. It's a source of energy and information, shining its story across the galaxy. In the deep quiet of space, our star continues its ancient work. It fuses hydrogen into helium, creates energy from matter, and shines steadily through the darkness. It has mastered the art of nuclear burning, achieving a stability that allows it to serve as the energy source for entire planetary systems. But this stability is not permanent. Deep in the star's core, the fuel is slowly being consumed. The helium ash continues to accumulate. The balance that has sustained our star for billions of years will eventually shift, triggering the next chapter in its evolution. The star will grow old, and in its aging, it will become something magnificent and strange. For now, though, the star burns on, patient and reliable. It has settled into the long, peaceful rhythm of main sequence life, where nuclear fusion provides steady energy and gravitational equilibrium ensures stability. It shines with the quiet confidence of a star in its prime, healthy, stable, and beautifully predictable. The light streaming away from our star carries more than energy. It carries the promise of complexity, the energy needed to power chemical reactions, drive weather systems, and perhaps even sustain life. Every photon is a messenger from the nuclear fires at the star's heart, a tiny packet of energy that can travel across light years to warm, distant worlds. As you rest tonight, remember that you are bathed in starlight, the energy that powers every biological process in your body originally came from nuclear fusion in stellar cores. You are, quite literally, made of star stuff, assembled from elements that were forged in the hearts of ancient suns. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created by stars like the one we've been following. Our star continues to burn, steady and reliable, in the vast ocean of space. It has found its rhythm and settled into the long, peaceful chapter of stellar life. For billions of years to come, it will continue this patient work, fusing hydrogen into helium and shining its light across the cosmos. But change is coming. Deep in the star's core, the hydrogen fuel is slowly being depleted. The helium ash continues to build up, growing denser and hotter. The delicate balance that has sustained our star for so long will eventually be disrupted. And when it is, our star will begin one of the most beautiful transformations in the universe. The end of the main sequence doesn't come suddenly. It's a gradual process that unfolds over hundreds of millions of years. As the hydrogen in the core is consumed, the nuclear fires begin to dim. Without the outward pressure from fusion reactions, gravity starts to win the ancient battle at the star's heart. The core begins to contract under its own weight. As it shrinks, it heats up, just as a gas becomes hotter when it's compressed. The rising temperature allows hydrogen fusion to continue in a thin shell around the inert helium core. This shell burns more vigorously than the core ever did, producing more energy than the star generated during its main sequence lifetime. The extra energy flowing outward from the hydrogen-burning shell has a dramatic effect on the star's outer layers. The increased luminosity causes the star's atmosphere to expand and cool. What was once a compact, hot, yellow star begins to transform into something far larger and redder. This is the beginning of the red giant phase, one of the most spectacular chapters in a star's life. Our star, which spent billions of years as a stable, well-behaved main sequence star, is about to become something magnificent and strange. The expansion happens slowly at first, then accelerates. The star's outer layers puff up like a balloon being inflated. The surface moves farther and farther from the nuclear furnace at the core, and as it does, it cools dramatically. The star's color shifts from yellow to orange to deep red. If our star had planets in close orbits, they would now find themselves in grave danger. The expanding stellar atmosphere could engulf them entirely, or at the very least subject them to intense heating as the star's surface draws near. Our star's habitable zone moves outward, potentially bringing warmth to worlds that were once frozen. As the red giant phase progresses, our star becomes enormous. It might expand to 100 times its original size, or even larger. If it were placed at the center of our solar system, its surface could extend past the orbit of Earth. Yet despite this incredible size, the star's surface is actually cooler than it was during its main sequence lifetime. The expansion creates beautiful consequences. The star's outer layers become tenuous, more like a hot, thin atmosphere than the dense plasma of a main sequence star. The star develops a gentle stellar wind, streams of matter flowing away from its surface and into space. This wind is much stronger than anything the star produced during its main sequence lifetime. The stellar wind carries away mass slowly but steadily. Over the course of the red giant phase, the star might lose 10 or 20% of its total mass. This material doesn't disappear. It becomes part of the interstellar medium, enriching the space around the star with heavier elements created by nuclear fusion. Deep inside the star, dramatic changes continue. The helium core, no longer supported by hydrogen fusion, continues to contract and heat up. The hydrogen-burning shell around the core becomes thinner and hotter, producing energy at an ever-increasing rate. The star becomes more luminous, sometimes hundreds of times brighter than it was on the main sequence. The structure of the red giant is remarkable. At the center lies a small, incredibly dense core of helium, perhaps the size of Earth, but containing a significant fraction of the star's mass. Around this core burns a thin shell of hydrogen fusion, producing prodigious amounts of energy. And surrounding everything is an enormous, tenuous envelope of cooler gas extending outward for millions of miles. Convection currents flow through the star's expanded envelope, carrying material from the interior to the surface. For the first time in the star's life, products of nuclear fusion can reach the surface directly. The star's atmosphere becomes enriched with helium and other elements created in its core, changing its spectral signature and revealing its nuclear history to any observing astronomers. The red giant phase is also a time of instability. The star pulsates, growing brighter and dimmer in cycles that can last months or years. Its surface heaves and flows like a slowly boiling liquid. The stellar wind varies in strength, sometimes increasing dramatically and carrying away large amounts of material. These pulsations are caused by the star's struggle to find a new equilibrium. The nuclear burning shell produces energy in bursts, and the star's enormous envelope responds by expanding and contracting. It's as if the star is breathing, inhaling, and exhaling matter and energy as it searches for stability. As the helium core continues to heat up, it approaches a critical temperature, 100 million degrees Celsius. At this temperature, helium nuclei move fast enough to overcome their mutual repulsion and fuse together. The process requires 3 helium nuclei to collide almost simultaneously, creating carbon in what's known as the triple alpha process. When helium fusion finally ignites, it happens suddenly and dramatically. The helium core undergoes what astronomers call the helium flash, a brief but intense period of nuclear burning that can produce as much energy as the entire galaxy. But this enormous energy release is absorbed by the star's outer layers and doesn't dramatically affect its appearance from the outside. The helium flash marks the beginning of a new phase in the star's evolution. Now the star has 2 nuclear burning shells, helium fusion in the core and hydrogen fusion in a shell around it. This dual core burning makes the star's behavior even more complex and unstable. The red giant phase is relatively brief compared to main sequence lifetime. While our star spent 10 billion years burning hydrogen steadily, it will spend only a few 100 million years as a red giant. It's a time of rapid change and dramatic evolution, a stark contrast to the steady reliability of the main sequence. During this phase, the star creates new elements through nuclear fusion. Carbon forms from the collision of 3 helium nuclei. Some carbon nuclei capture additional helium nuclei to form oxygen. The star becomes a factory, for the heavy elements that will one day form rocky planets and enable complex chemistry. The stellar wind continues to carry away material, gradually reducing the star's mass. This wind is enriched with the heavy elements created in the star's interior, spreading carbon, oxygen, and other elements into the surrounding space. The star is giving back to the galaxy, returning processed matter to the interstellar medium. The red giant's enormous size makes it a prominent feature in its local neighborhood. Its light can be seen across vast distances, and its stellar wind influences the space around it for light years in all directions. It's no longer the quiet, well-behaved star it once was, but a dramatic presence that commands attention. The star's magnetic field also changes during the red giant phase. The expanded envelope and complex internal structure create new magnetic phenomena. The star might develop powerful magnetic loops that extend far beyond its surface, channeling matter and energy in spectacular ways. As the red giant continues to evolve, it faces an uncertain future. Stars like our Sun, with masses similar to our own, will eventually shed their outer layers entirely, creating beautiful planetary nebulae and leaving behind white dwarf remnants. More massive stars face even more dramatic fates, potentially exploding as supernovas or collapsing into neutron stars or black holes. But that's still in the future. For now, our star revels in its red giant phase, expanded and luminous, pulsating gently as it burns helium in its core and hydrogen in its shell. It has transformed from a steady main sequence star into something magnificent and dynamic, a cosmic beacon that announces the ongoing alchemy of stellar evolution. The red giant phase is a time of beauty and complexity. The star's enormous size and cool surface temperature give it a deep red color that's stunning to behold. Its pulsations create rhythmic changes in brightness that mark the passage of stellar time. And deep within, nuclear fires continue to forge new elements and release energy on a scale that dwarfs anything we can imagine. This phase also represents the star's generosity. Through its stellar wind, it returns material to the galaxy, enriched with the heavy elements it has created. This matter will one day become part of new stars, planets, and perhaps even living organisms. The star is participating in the great cosmic cycle of matter and energy that connects all things in the universe. Our red giant continues to burn, expanded, and luminous as it navigates this new chapter of stellar evolution. It has left behind the steady reliability of its main sequence lifetime and embraced the dynamic complexity of old age. It pulses with nuclear fire, shines with red light, and slowly disperses its outer layers into space. But even this magnificent phase cannot last forever. The helium in the core will eventually be consumed, just as the hydrogen was before it. When that happens, our star will face its final transformation, the last act in its billion-year drama of nuclear evolution. The death of a star is not really death at all, but transformation. As our red giant continues to age, the nuclear fuel in its core slowly depletes. The helium that sustained its second youth burns away, creating carbon and oxygen in the star's heart. Without the energy from fusion to support it, the core begins its final contraction. Meanwhile, the star's outer layers become increasingly unstable. The stellar wind grows stronger, carrying away material at an accelerating rate. The star pulsates more violently, sometimes dimming dramatically as clouds of dust condense in its cooling atmosphere, then brightening again as the dust disperses. These pulsations gradually become so strong that they overcome the star's gravity entirely. The outer layers, no longer bound to the star's core, begin to drift away into space. This process happens slowly at first, then accelerates as more and more material is lost. What emerges from this gentle dissolution is one of the most beautiful sights in the cosmos. A planetary nebula. Despite its name, it has nothing to do with planets. These nebulae were named by early astronomers who thought their round, disc-like appearance resembled planetary discs when viewed through small telescopes. A planetary nebula is essentially the outer atmosphere of a dying star, illuminated from within by the hot stellar core that remains. The gas glows in brilliant colors, red from hydrogen, green from oxygen, blue from helium, creating intricate patterns that rival any work of art. Some planetary nebulae look like eyes, others like butterflies or flowers. Each one is unique, shaped by the specific conditions of its parent star's death. At the center of this glowing shell of gas sits the star's final form, a white dwarf. This is what remains when all the outer layers have been stripped away, leaving only the hot, dense core. A white dwarf is about the size of Earth, but contains roughly the mass of our Sun. It's one of the densest objects in the universe. A teaspoon of white dwarf material would weigh as much as a car. The white dwarf is supported not by nuclear fusion, but by electron degeneracy pressure. This is a quantum mechanical effect that prevents electrons from being packed too closely together. It's the ultimate expression of the Pauli exclusion principle, the quantum rule that says no two electrons can occupy the same state. This pressure is strong enough to support the white dwarf against gravitational collapse. When it first forms, a white dwarf is incredibly hot, perhaps 100,000 degrees Celsius at its surface. It shines brilliantly with white-hot light, hence its name, but it has no fuel left to burn. Its only energy source is the heat stored from its formation. Like a cooling ember, it will gradually radiate this heat away over billions of years. The cooling process is extraordinarily slow. A white dwarf will remain hot for longer than the current age of the universe. It will slowly fade from white to yellow to red, and eventually to a cold, dark object called a black dwarf. But the universe is not yet old enough for any black dwarfs to exist. Even the oldest white dwarfs are still glowing faintly. The surface of a white dwarf is a strange place. The gravity is so intense that it would instantly crush any normal matter. The surface itself might be made of crystallized carbon, essentially diamond, formed under the incredible pressure. The atmosphere, if any exists, would be incredibly thin and composed of the lightest elements like hydrogen or helium. Some white dwarfs have been found to have unusual compositions. Their surfaces show traces of heavier elements like oxygen or carbon, suggesting that these elements have floated to the surface over time. Others show signs of having accreted material from companion stars or from the surrounding planetary nebula. The magnetic field of a white dwarf can be incredibly strong, sometimes millions of times more powerful than Earth's magnetic field. These fields can channel matter and energy in complex ways, creating hotspots on the surface and affecting how the white dwarf cools. White dwarfs are also remarkably stable. Once formed, they can exist essentially unchanged for trillions of years. They represent the final equilibrium for stars like our Sun, a perfect balance between gravity pulling inward and electron degeneracy pressure pushing outward. The planetary nebula surrounding the white dwarf gradually expands and fades. Over thousands of years, it spreads through space, mixing the heavy elements created in the star's interior with the interstellar medium. This enriched material becomes available for the formation of new stars and planets. This is how stars give their gift to the universe. Through their deaths, they scatter the elements necessary for complexity and life. The carbon in our bodies, the oxygen we breathe, the calcium in our bones, all of these elements were created in stellar cores and dispersed through space by dying stars. But our star's story doesn't end with its transformation into a white dwarf. The white dwarf continues to exist, slowly cooling in the depths of space. If it's part of a binary system with another star, it might experience a second lease on life through interactions with its companion. Sometimes material from a companion star can fall onto the white dwarf's surface. This material, compressed and heated by the white dwarf's intense gravity, can undergo nuclear fusion in explosive events called nova. These explosions don't destroy the white dwarf, but they can make it briefly shine thousands of times brighter than normal. In rare cases, if enough material accumulates on the white dwarf's surface, it can trigger a catastrophic explosion called a Type Ia supernova. This explosion completely destroys the white dwarf, scattering its material across space, and creating even more heavy elements for future generations of stars. But for most white dwarfs, the future is quiet. They will simply continue cooling, gradually fading from view over timescales that dwarf the history of the universe. They are the universe's longest-lived objects, cosmic embers that will outlast galaxies and black holes. The white dwarf phase represents a kind of stellar immortality. While the original star died when it shed its outer layers, the white dwarf will persist for trillions of years. It carries within its crystalline structure the memory of the star that created it, its mass, its composition, its history, written in the physics of its formation. Our white dwarf drifts quietly through space, a Earth-sized remnant of a star that once shone for billions of years. It's incredibly hot, but slowly cooling. Incredibly dense, but stable. A testament to the extraordinary physics that governs stellar evolution. Around it, the planetary nebula continues to expand, carrying the star's legacy to distant regions of the galaxy. The nebula will eventually fade and disperse, but its material will endure, incorporated into future generations of stars and planets. This is the genteel death of a sun-like star, not a violent explosion, but a gradual transformation from a nuclear furnace into a cooling ember. It's a death that enriches the universe, spreading heavy elements far and wide, creating the conditions for complexity and life. The white dwarf will continue its billion-year cooling process, slowly fading but never truly dying. It represents the final victory of quantum mechanics over gravity, a stable endpoint where the star's core can rest for cosmic ages. But this peaceful ending is not the fate of all stars. More massive stars face far more dramatic destinies. When a star much more massive than our Sun reaches the end of its nuclear burning lifetime, the result is not a gentle puffing off of outer layers, but one of the most violent events in the universe. For a star more than 8 or 10 times the mass of our Sun, the death throes are spectacular beyond imagination. These massive stars burn through their nuclear fuel much more quickly than their smaller cousins. Where a sun-like star might burn hydrogen for 10 billion years, a massive star might exhaust its fuel in just 10 million years. But massive stars have a trick that smaller stars lack. They can burn more than just hydrogen and helium. As the core temperature rises, they can fuse carbon into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. Each stage of fusion releases less energy than the previous one and burns for a shorter time. The star develops an onion-like structure, with different fusion reactions occurring in concentric shells around the core. Hydrogen burns in the outermost shell, helium in the next shell inward, then carbon, neon, oxygen, and silicon. At the very center lies a growing core of iron. Iron is the stellar equivalent of ash. It cannot be fused to release energy. In fact, fusing iron requires energy rather than producing it. When the iron core reaches a critical mass of about 1.4 times the mass of our sun, disaster strikes. The core collapses catastrophically. In less than a second, it shrinks from the size of Earth to a ball only 20 kilometers across. The protons and electrons in the core are crushed together, forming neutrons and releasing a flood of neutrinos. The gravitational energy released in this collapse is enormous, more than our sun will produce in its entire 10 billion year lifetime. The collapse happens so quickly that the outer layers of the star haven't had time to react. They're still falling inward when the core bounces back, now supported by neutron degeneracy pressure. The collision between the infalling outer layers and the rebounding core creates a shock wave that propagates outward through the star. This shock wave triggers one of the most violent events in the universe, a core collapse supernova. The explosion is so energetic that for a brief time, the dying star can outshine an entire galaxy of 100 billion stars. The energy released is almost beyond comprehension, more than our sun will produce in its entire lifetime, released in just a few seconds. The supernova explosion accomplishes something that no other cosmic event can. The tremendous heat and pressure created in the explosion forge elements heavier than iron, elements like gold, platinum, and uranium that cannot be created in normal stellar fusion. These rare, heavy elements are scattered into space by the explosion, enriching the interstellar medium. The explosion also creates and disperses enormous quantities of the lighter heavy elements: carbon, oxygen, silicon, iron. A single supernova can produce more heavy elements than 1,000 normal stars create in their entire lifetimes. It's a cosmic forge operating on a scale that defies imagination. But the supernova is not just about destruction and dispersal, it also creates. The shock waves from supernovas compress nearby gas clouds, triggering the formation of new stars. The heavy elements they scatter become incorporated into these new stars and their planetary systems. Supernovas are thus both destroyers and creators, ending stellar lives, but enabling new ones. At the center of the explosion, something remarkable remains. The core that collapsed to trigger the supernova doesn't disappear. It's compressed into a neutron star, one of the most extreme objects in the universe. A neutron star is only about 20 kilometers across, small enough to fit inside a large city. But it contains more mass than our sun. It's so dense that a teaspoon of neutron star material would weigh 1 billion tons. The entire star is essentially a giant atomic nucleus, made almost entirely of neutrons packed together at nuclear density. The surface of a neutron star is a place of extremes. The gravity is so strong that if you dropped an object from a height of 1 meter, it would hit the surface traveling at 2,000 kilometers per hour. The magnetic field can be 1 trillion times stronger than Earth's, powerful enough to distort the shape of atoms. Despite their incredible density, neutron stars spin. Some rotate hundreds of times per second, their surfaces moving at a significant fraction of the speed of light. As they spin, they emit beams of radiation from their magnetic poles. If these beams sweep across Earth, we detect regular pulses of radio waves, X-rays, or gamma rays. These rotating neutron stars are called pulsars, and they're among the most precise timekeepers in the universe. Their pulse periods are so regular that they rival atomic clocks in their accuracy. Astronomers use pulsars as cosmic lighthouses, using their precise timing to study everything from gravitational waves to the structure of space and time. Neutron stars are also laboratories for extreme physics. They contain matter in states that cannot be replicated on Earth. In their cores, the pressure might be so intense that ordinary matter breaks down into exotic forms like quark matter or strange matter. They test our understanding of physics at the very limits of density and pressure. Some neutron stars exist in binary systems with normal stars. Material from the companion star can fall onto the neutron star's surface, where it undergoes explosive nuclear fusion. These events, called X-ray bursts, can briefly make the neutron star shine as brightly as 100,000 suns. When two neutron stars orbit each other, they gradually lose energy by emitting gravitational waves, ripples in space-time itself. Eventually, they spiral together and merge in a catastrophic collision that creates more gold and platinum than any other known process. These neutron star mergers are responsible for much of the heavy elements in the universe. The neutron star represents the ultimate triumph of the strong nuclear force over gravity. Where white dwarfs are supported by electron degeneracy pressure, neutron stars are held up by neutron degeneracy pressure and the strong force that binds neutrons together in atomic nuclei. But even neutron degeneracy pressure has its limits. If the collapsing stellar core is too massive, more than about 3 times the mass of our Sun, not even neutron degeneracy pressure can stop the collapse. The star continues shrinking, and gravity becomes so strong that nothing, not even light, can escape. This is how black holes are born from the deaths of the most massive stars. The stellar core collapses to a point of infinite density called a singularity, surrounded by an event horizon, the boundary beyond which nothing can return. A stellar mass black hole might be only tens of kilometers across, but its gravitational field dominates the surrounding space. Matter falling into a black hole heats up to millions of degrees and emits brilliant X-rays before crossing the event horizon and disappearing forever. Black holes represent the ultimate victory of gravity over all other forces. They are regions where space-time itself is so curved that it closes back on itself. They're not really holes, but rather incredibly dense objects whose gravity is so strong that they trap everything, including light. The formation of a black hole is perhaps the most extreme event possible in stellar evolution. The massive star, after burning through its nuclear fuel in just a few million years, ends its life in a supernova explosion so violent that it can be seen across the universe. Yet at its heart, it creates something so dense and dark that it becomes invisible, known only by its gravitational effects. These stellar mass black holes are scattered throughout the galaxy, the remnants of ancient massive stars. Most are invisible unless they're actively feeding on nearby matter. But they're there, dark sentinels marking the places where the most massive stars once burned bright and then collapsed into singularity. The death of massive stars is thus a tale of extremes. From lives measured in mere millions of years to explosions that can be seen across the cosmos. From the creation of neutron stars with unimaginable density to black holes, where space-time itself breaks down. These stellar deaths are cosmic catastrophes that paradoxically create the conditions for future complexity and life. The heavy elements forged in stellar cores and scattered by supernovas are essential for rocky planets and biological chemistry. The shock waves from supernovas trigger the formation of new stars. Even black holes and neutron stars play important roles in galactic evolution, influencing the motion of gas and stars around them. And so the cycle continues. Stars are born, live, and die, each contributing to the cosmic evolution of matter and energy. The universe grows more complex with each stellar generation, accumulating heavy elements and creating the conditions for planets, chemistry, and life. But perhaps the most remarkable aspect of stellar death is that it's not really an ending. The matter and energy of dying stars don't disappear. They're recycled into new stars, new planets, new possibilities. The universe operates as a vast recycling system where every atom has passed through multiple stellar generations. The calcium in your bones was forged in the core of a dying star. The iron in your blood was created in a supernova explosion. The oxygen you breathe was made when helium nuclei collided in a stellar furnace. You are quite literally made of star stuff, assembled from the ashes of ancient suns. This is the gift that dying stars give to the universe. Through their deaths, they enable complexity, chemistry, and life. They transform simple hydrogen and helium into the rich tapestry of elements that make planets and people possible. As you rest tonight, remember that you are connected to this cosmic story. The elements in your body were forged in stellar cores over billions of years. You are part of the universe's long journey from simplicity to complexity, from hydrogen and helium to chemistry and consciousness. The stars continue their ancient dance of birth and death, creation and destruction, transformation and renewal. Each stellar generation builds on the last, creating ever more complex combinations of matter and energy. It's a story that connects the largest scales of space and time to the most intimate details of your existence. And in the quiet darkness of space, new stars are being born even now. In the cold depths of molecular clouds, gravity is gathering matter and preparing the next generation of stellar furnaces. The cycle continues, eternal and beautiful, driven by the simple but profound physics of matter, energy, and gravity. The story of stellar death is thus also a story of stellar birth. Every ending enables a new beginning. Every death feeds new life. In the cosmos, nothing is ever truly lost. It's simply transformed into new forms, new possibilities, new chapters in the ongoing story of the universe. The universe breathes with the rhythm of stellar birth and death. In the cold depths of space, new stars are always forming, gathering matter and igniting nuclear fires. At the same time, older stars are ending their lives, returning their processed material to the cosmos. It's a cycle that has continued for over 13 billion years, slowly enriching the universe with heavy elements and complexity. This cosmic recycling happens on timescales that dwarf human comprehension. A single stellar generation might last billions of years, yet from the universe's perspective, it's all one continuous process of transformation and renewal. The interstellar medium, the thin gas and dust that fills the space between stars, serves as the reservoir for this cycle. It's enriched by dying stars and depleted by star formation, stirred by supernova shock waves and organized by magnetic fields. This medium is far from empty. It's a dynamic, evolving component of the galaxy that carries the chemical history of stellar evolution. Within this medium, the heavy elements created by past generations of stars mix and combine. Carbon from dying red giants mixes with oxygen from supernovas. Iron from stellar cores combines with gold from neutron star mergers. Over time, the interstellar medium becomes a rich chemical soup, ready to feed the formation of new stars and planets. When new stars form from this enriched material, they can create rocky planets like Earth. These planets inherit the chemical legacy of countless previous stellar generations. The solid worlds where chemistry can flourish and life might emerge are thus the grandchildren of ancient stars. The solar system formed from material that had been processed through multiple stellar generations. The Sun is what astronomers call a third-generation star, formed from gas that had already been through at least 2 cycles of stellar evolution. This is why the Earth contains the heavy elements necessary for geology, chemistry, and biology. But stellar nucleosynthesis continues even today. At this very moment, stars throughout the galaxy are forging new elements in their cores. Red giants are creating carbon and oxygen. Massive stars are building up to iron. Supernovas are exploding and scattering fresh heavy elements into space. This ongoing nucleosynthesis means that the universe is still evolving chemically. Each stellar generation is slightly more metal-rich than the last, enabling the formation of more complex planets and perhaps more sophisticated forms of life. The process also means that different regions of the galaxy have different chemical compositions. Areas near active star formation regions are enriched with fresh, heavy elements. Regions in the galactic halo, where star formation ceased long ago, remain relatively metal-poor. This chemical evolution has important implications for the possibility of life. Early in the universe's history, when only hydrogen and helium existed, rocky planets were impossible. It took billions of years of stellar evolution to create enough heavy elements for Earth-like worlds to form. Even today, the process continues. Future generations of stars will be born from material even richer in heavy elements than our Sun. They might be able to form planetary systems with compositions we can barely imagine. Worlds rich in rare elements that could enable entirely new forms of chemistry and complexity. The cycle of stellar birth and death also affects the large-scale structure of galaxies. Supernova explosions inject energy into the interstellar medium, driving turbulence and regulating star formation. They can blow gas out of small galaxies entirely, affecting their evolution over cosmic time. Stellar winds from massive stars and white dwarfs also contribute to the stirring of the interstellar medium. They create bubbles and cavities in the gas, channels through which later generations of stars can form. The magnetic fields generated by stars also play a role in galactic evolution. They thread through the interstellar medium, affecting how gas flows and collapses. They can support gas clouds against gravitational collapse or trigger star formation by concentrating material along field lines. All of these processes work together to create the complex, dynamic, evolving structure we see in galaxies today. Galaxies are not static collections of stars. They're living systems where gas, dust, stars, and energy interact in intricate ways across billions of years. The Milky Way itself bears the scars and signatures of this ongoing stellar evolution. The spiral arms are outlined by young, hot stars and star-forming regions. The galactic halo contains the oldest, most metal-poor stars. The central bulge shows evidence of ancient star formation and chemical enrichment. By studying the distribution of different stellar populations, astronomers can reconstruct the history of galactic evolution. They can trace how the Milky Way assembled over billions of years, accreting smaller galaxies and evolving from a chaotic early state into the organized spiral we see today. This history is written in the chemical compositions of stars. The oldest stars in the halo have the signatures of the first generation of massive stars, those that formed from pure hydrogen and helium and enriched the universe with the first heavy elements. Intermediate-age stars in the disk show the effects of gradual chemical enrichment over billions of years. The youngest stars in the spiral arms are the most metal-rich, formed from material that has been processed through many stellar generations. Even our own sun carries this chemical history. By studying its composition, astronomers can infer what the interstellar medium was like 4.6 billion years ago when the solar system formed. They can trace how the sun's birth cloud was enriched by previous generations of stars. The planets of the solar system also preserve this chemical record. Meteorites, which are fragments of asteroids that formed early in solar system history, contain tiny grains of material that actually predate the solar system. These pre-solar grains were condensed in the atmospheres of dying stars and survived the formation of the solar system intact. By studying these grains, scientists can learn about the specific stars that contributed material to the solar system's formation. They can identify grains that came from red giants, supernovas, and even rare types of stars like Wolf-Rayet stars. This detailed chemical archaeology reveals the complex heritage of the material that makes up our world. Every element in your body has a stellar origin story. Some atoms were created in the steady hydrogen burning of main sequence stars. Others were forged in the violent explosions of supernovas. Still others were produced in the exotic conditions of neutron star mergers. The diversity of stellar death mechanisms means that different elements are produced by different processes. Light elements like carbon and oxygen come primarily from the deaths of medium-mass stars. Iron is produced mainly in core collapse supernovas. The heaviest elements like gold and uranium require the extreme conditions of neutron star mergers. This diversity of origins is what makes the chemical richness of the universe possible. No single type of star or stellar death can produce all the elements needed for complex chemistry and life. It takes the full spectrum of stellar evolution to create the periodic table of elements. And the process is ongoing. At this very moment, stars are dying throughout the universe, each one contributing its unique chemical signature to the cosmic mix. Red giants are shedding carbon-rich winds. Massive stars are exploding as supernovas. Neutron stars are spiraling together and merging. Each of these events adds to the universe's growing inventory of heavy elements. The cosmic abundance of elements like carbon, oxygen, and iron continues to increase as more stars complete their evolutionary cycles. This ongoing enrichment has important implications for the future of life in the universe. As the universe becomes more metal-rich, it becomes increasingly capable of supporting complex chemistry and biology. Future generations of stars and planets will have access to element combinations that were impossible in the early universe. But the process also has limits. Star formation cannot continue forever. Eventually, the universe will run out of hydrogen to fuel new stars. When that happens, stellar evolution will cease, and the cosmos will begin its long decline into darkness. That endpoint is still trillions of years in the future, so far away that it's essentially irrelevant to any life that might exist today. For now, the cycle of stellar birth and death continues, driven by the vast reservoirs of hydrogen left over from the Big Bang. And in that continuing cycle, each star plays its part. Whether it's a small red dwarf that will burn for trillions of years, or a massive blue giant that will explode in just a few million years, every star contributes to the ongoing chemical evolution of the cosmos. The story we've followed tonight, from the birth of a star in a cold molecular cloud to its final transformation into a white dwarf, neutron star, or black hole, is a story that has played out countless times throughout the universe. Each iteration adds to the cosmic inventory of elements and energy, building the foundation for future complexity and life. As you drift towards sleep, remember that you are part of this cosmic story. The elements in your body were forged in stellar cores and scattered by stellar deaths. You are made of star stuff, assembled from the ashes of ancient suns that lived and died long before our solar system existed. The stars continue their ancient work, burning hydrogen into helium, creating energy and elements, living and dying in an endless cycle of transformation. They are the universe's chemists, slowly building up the periodic table, one fusion reaction at a time. In the quiet darkness of space, new stars are being born while old ones fade away. The cosmic cycle continues, patient and persistent, creating the conditions for chemistry, complexity, and consciousness. It's a process that connects the largest scales of space and time to the most intimate details of existence. And somewhere in the vast cosmos, perhaps orbiting a distant star born from material enriched by countless previous stellar generations, other forms of life might be looking up at their own night sky, wondering about the stars and their own connection to the cosmic story. The universe is vast and full of wonders, driven by the simple but profound physics of gravity, nuclear fusion, and quantum mechanics. Stars are its engines of transformation, converting hydrogen into complexity, matter into energy, and simplicity into the rich tapestry of elements that makes everything possible. Tonight, as you rest beneath the light of distant stars, you are participating in this cosmic story. You are star stuff contemplating stars, matter organized into consciousness, and wondering about its own origins. In you, the universe has found a way to know itself, to understand its own story, through the remarkable emergence of life and mind. The stellar fires that forged your atoms continue to burn throughout the cosmos. The cycle of stellar birth and death continues its ancient rhythm, and in that continuing cycle, new possibilities emerge, new forms of complexity arise, and the universe's long journey from simplicity to sophistication continues. Sleep well, knowing that you are connected to the stars above and the cosmic processes that created everything. In your dreams, you might journey among the stars, witnessing their births and deaths, their patient work of transformation and creation. You are part of their story, and they are part of yours, in the grand, interconnected tapestry of the cosmos. The stars shine on through the night, ancient and patient, continuing their billion-year work of creation and transformation. They are the universe's gift to itself, engines of change that make complexity, chemistry, and consciousness possible. In their light, we find our connection to the cosmos and our place in the ongoing story of existence. And in the gentle darkness of space, the cycle continues, eternal and beautiful, driven by the fundamental forces that shape all things. Stars are born, live, and die, each one contributing to the universe's slow evolution toward greater complexity and possibility. Rest now, star child, in the knowledge that you are part of this magnificent cosmic story. The elements that make you possible were gifts from ancient stars, and their legacy lives on in you. The universe continues its patient work, creating new wonders, new possibilities, new chapters in the endless story of stellar transformation. The night sky above holds countless stars at every stage of evolution. Some are just beginning their nuclear lives, others are middle-aged like our sun, and still others are dying or already transformed into white dwarfs, neutron stars, or black holes. Each represents a chapter in the cosmic story of stellar evolution, a story that connects us all to the deep history and ongoing transformation of the universe. Sleep peacefully under their light, knowing that their story is your story. Their elements are your elements, and their patient work of transformation continues in every heartbeat, every breath, every thought. You are star stuff, beautifully organized into consciousness, part of the universe's long journey toward understanding itself. Good night.